Hello, so today we are doing this problem called remove the nth node from end list. And the problem says we get a linked list and we want to remove the nth node. And return the head. So for example, nth from the end, not just the end from the beginning. So for example, for this one, the second from the end, which means counting from the end backwards, it's this 4. And we start counting from 1. So 5 is the first, 4 is the second, so we want to remove the nth one, so we remove 4, and we end up with 1, 2, 3, 5. The problem is saying that n will always be valid, so there is always an nth element from the end. And can we do this on one pass? So let's start exploring this problem and see what we can do. So the first simple thing we can think of, let's take the linked list and see the first thing we can do. So the first thing we can do is just compute the length, and that we can do that in one pass. So this would be the straightforward solution. So compute the length, which is open time, and that will give us 5 elements, right? 5 length, right? Let's call this length, and let's call it maybe C, for example. And then after that, we need to find the nth from the end, and nth from the end, that's just equivalent to length minus n, which is in our case here C minus n, right? But since we want to remove it, to be able to remove a node, we need the node before it, right? We need a pointer to a node before it. Why is that? Because if we want to remove 4, if we have just a pointer at 4, I mean, what can we do? We can't do anything, because ultimately the final result we are aiming at is something like this, destroying this link with this 4 and making 3 just point to 5, right? So we need a pointer to 3 so that we can point it to 5, and so that 4 just get garbage collected, right? So we need actually a pointer to the element before, so that we can just say 3.next is now equal to 5, right? So we need a node, a pointer to 3, so that we can say its next is, so let's say node, let's say this pointer is node. Then we need to be able to say node.next is equal to node.next. Or let's say this is current pointer, that would make it more clear. So this is the current pointer, then deleting the node current.next would mean just making current.next of this one points to current.next, right? And that would effectively delete the node, right? So which means that we need to just keep advancing from the head until C minus n minus 1, then do this, right? Advancing current that starts from the head, and then do this, right? That's pretty much all we need to do. So let's code this solution up. So first we need to find the length. So let's call it C. Start out as 0, right? And then we need to have some node that is pointing to the head so that we can find the length, right? So first we are just going to find the length, so it points to head, and then we'll say while current, we want to count the number of nodes. So what we need to do is say increment when we haven't reached nil yet, and say current is equal to current.next. So this essentially counts the length and put it at C. Now what we want is advance K, advance C minus n minus 1 step, right? And so while K is bigger than or equal to 0, we want to keep advancing, right? But in order to get a current here, we need to put it back at head, because right now it's reached the end to calculate the length. So we need current to be at head again. And then this way we can say current equal to current.next, and we can subtract 1 from K. And then when we reach this here, since we are doing C minus n minus 1, we will be at the node before. And so we can just do this operation, right? And then at the end we can just return. But you can see our problem here. We should return the head, but we no longer have, because sometimes maybe they said, like, let's say with this, maybe n was, let's see, we have 3, 4, 5, maybe n was 5, right? So we'll remove the head. So what we want to return is this, right? So we can't just return the head, right, like this, because sometimes that's what we literally removed, right? So the head would be just alone. And so to encounter this, the usual trick with linked lists is to create a dummy node to keep hold of that, of the entire list, so that if we remove the head, so we can have something like this. So in case of n equal to 5, we would have a node dummy that is just 0. So this would be just dummy. And then it points to the rest, so that if we remove 1, what we will end up with is the following. We will end up with this, right? So that, and then we can just return dummy.next, which will make us return just this, right? And so that's a clever way to handle this special case of the first node is the one that we want to remove. Always when doing a solution on a linked list, we should check what does happen if the element we are solving for is for a specific edge case is the head, or sometimes also is the tail. In this case, if it's the tail, it will be fine because we find the element before it and just we put it next to nil, so that's fine. In the head here, the usual trick that gets the job done is doing this dummy node. And so in our case here, our dummy node is just list node of 0. And instead here, we can just return dummy.next. And that should do it. Yes, so let's run this and see how it works, if it works. We get an empty list, so there is a problem somewhere here. Yes, the problem is I created dummy, but I didn't assign its dummy.next to head, which is doing this. So we should do this so that, because otherwise I just have these separated and dummy.next is just null, right? So yeah, that was a mistake. Okay, so we have a problem here. Let's see. So let's just do this c minus n, and since we are doing c minus n, we will wait until it reaches 0, and then we'll keep subtracting so we get the node before. And here we are counting c plus 1, so that's good. And our current starts out as head, so that's also good. But our current here should start out at dummy because of this case here. Because the case of if it's the first element, we want the current to start at dummy so that we can count just 1, because we are starting. So if for a case like, let's say for a case like this, where we have just one node, let's say we have just one node and n equal to 1. So in this case we should return null, right? But that won't happen if we assign to current head, right? So here I'm assigned to current head, and since I'm doing bigger than 0, when it reaches 0 it will get out, and I will have a reference to dummy in the current, and so when I do this it will point to dummy.next, right? Okay, so that works. Let's submit. Okay, so that passes, and essentially this one, the complexity, we're just traversing the list here, and we are traversing at most the length of the list here, so at most is going to be the length of the linked list, right? Let's call it O of M, right? The length of linked list. But even though it's in terms of time complexity it's O of M, we are still doing 2 loops. So let's think if we can do better by just doing 1 loop. And so how can we think about a solution like that? So the idea for that is the following. So we want the nth from the end, right? That's what the problem is asking. So so what does this mean? That means if we have a pointer to the end and we have another pointer, let's say something here, let's call it something, let's just call it P, right? Let's call this P1 and let's call this one P2, which is at the end, right? So what do we want to happen? We want the gap here between the two to be n. We want the gap to be n. So let's call this gap. Should be n, because that what it means. What nth from the end means the gap between the nth. Basically, this nth from the end is equivalent to gap between the node. So we want node that is nth from the end. So gap between node and end is equal to n. That's literally what it means. So this is what we want to do. So what we can do to achieve this is just make them both start at the same place, right? P2 and P1, and then advance only P2 by n step, right? And at that point, if we advance it only by n step, let's say n is 3, then the gap here, we know that it's n, right? So this is the case where n equal to 3. And after that, we keep advancing them at the same pace so that we can preserve this gap of n, right? So we do this, we move this here, move this here. So we need to move P1 one step so that we can preserve that n gap. And then we keep doing that. Now we have n gap. Now when we reach this point here, the end, we have n gap, right? We have n is the gap between the two. So, and this one reaches the end. So right away we know our pointer we are looking for is this, because we maintain the gap and this one reaching the end, and the definition is that the gap between the node and the end is the end. So we achieved that and our solution is done. There is only one thing to think about after doing this, is that, okay, once we did this, actually to remove the node, what we need is not a reference to the node itself. We need a reference to the node before it. And so to do that, that's simple. Just change what we did a little bit and maintain a gap of n plus 1, right? So that at the end, this one would be at null. And the gap here would be n plus 1, and this one would be at the position just before, which is 2. And that way we can just assign 2 to before, and that way effectively we deleted the nth element. And so this is what we are going to write right now. So let's start right away. So that would mean here we need P1 and P2 as our pointers. And the same thing we did earlier, which is to handle the case of it's the first node, the head that we want to remove, then we need to do something a little bit different. But let's first just think about this. So here at most we advance the list by n times, right? At most we advance the pointer P2 n times, and then pointer P1 at pointer P2 at the length of the linked list times, and then P1 length of n. And n is certainly smaller or equal to the length of the linked list. So our time complexity here is just length of linked list, which let's just call that m. So our time complexity is just O of m. So it is the same order as the previous solution, but we are just using one loop. So we need, in the same way as the previous loop, we need a dummy node that holds 0 and that the head is pointing its next pointer to the head, and we initialize both of them to dummy. So that, notice when we assign both to dummy, that changes because now it's plus 1 in this case, right? So we need to keep that in mind. And so to create the gap of n, we just, while n is bigger than 0, so if we stop only when n reaches 0, so what we are doing here is n plus 1 steps, right? And so and we are keeping the gap of n plus 1 in this case, right? So we have this here, p2.next, and now, so we create the gap of n, of size n plus 1, and then we, once we do that, we keep checking np2.next. So now we move both at the same speed until p2 reaches null, right, in this case. And so now we advance them at the same pace. So advance while we haven't reached the end, reach it after the end, which is nil. Keep advancing both pointers at the same speed, keeping gap of n plus 1. So that would mean we need p2.next and we need p1 to be p1.next, right? And then to remove, since we said that by doing this n plus 1, we have the element just at the before node, before the one we can delete. Now we can just say p1.next is equal to the same way we did before, essentially. And this way we are deleting the nth element, and then after that we need to return dummy.next, because that's what the linked list we have is, right? And so that seems like it works. Okay, so that passes. And this solution is O of n also, because at most we'll go through the O of m, because at most we'll go through the list just once. So there is another way to do this, which is always often with a linked list problem there is a recursive solution. So let's think about, in our case here, what recursive solution can we do? So recursive solution means we need a base case, we need recurse on a smaller input size, right? And we need what operation that combine results, right? And so what is the base case? It's a linked list, so the base case is often when the head is null, when the node is null. So if node is null or none in Python, in that case, and this is just equivalent to not node, in that case, what will we do? In that case, we'll just return while the position is 0, and so we want the goal from my recursion would do something clever where it will return. I want my recursion method to return index and the pointer to where we are at. Why is this helpful? Because I want the index to be able to check if I'm at n, if I'm at position n, right? And then I want a pointer to the remaining list, right? So I can recurse on the rest. Why am I doing that? Because I just want to remove I want to know when I reach n, I want to remove that node, because that's what I want to get rid of. So the way I'm going to remove it is just by not returning its next instead of returning it, right, to the caller, right? So here, to remove the node at n, just return its next to the caller. That will make it its next. So basically, the way it works is my recursion would do something like where it has a head.next that is waiting for the result of the call of the recursion call, right? And so if I return node.next, instead of returning node, that means the value at node got skipped, because the next will be pointing to its next. So we are essentially doing the same we did earlier, except with recursion here, right? And so also naturally with linked list, my smaller input size would be the head.next or node.next, right? And let's just call it remove. So I'm going to try to remove the position at node.next, right? And what is the operation combine? It's just assigning this to whatever result I got, right? And then I will get the position. And so I would check if I plus 1 equal to n, which means the next iteration I'm at position n. At that point, I can just return the next to the caller, which means I'm going to return to you that the position is I plus 1, but the actual element at that position is no longer node because I want to remove that, so it's actually node.next. But if it's not, then I don't want to remove the node, so I just tell my caller point yourself to node instead, which is it point yourself to node so that I didn't remove it. But in the case where it's equal to n, I'm removing it, so I'm telling my caller point to node.next instead. And so this is the gist of this method. So we need the helper function that, let's call it just remove node, and we will do our base case and everything, but here we need to return something. And so if not node, which is our base case, we want to return the index is 0 and it's just head, that's the node, there is nothing to remove. Otherwise, I'm going to call my function recursively and get a node.next, right, to point to whatever the call returns. So I will be pointing to it because that's the element after me. And then now I check if for me I plus 1 is equal to n. If that's the case, then this is nth from the end, right? Because this is kind of traversing it backward. When it gets to the head is 0, and then the element when it gets to the last one is 0, so the element before it adds plus 1, so that's 1, and so the element before that is 2. The element before, so basically when I reach it here, my recursion goes down, and when it reaches here, the index is 0. When it reaches here nil, the index is 0. And so the recursion, when the recursion stack goes up, then here I'm at 1, right? And then I keep going, here I'm at 2. And so you can see in my recursion, every time I go up, it's I plus 1, which is why I'm doing this. And when it, let's say n was 3, right? And so when I go here, I'm at 3, so I want to remove this. So if I want to remove this, what do? I just return to my caller 4 and say, okay, you point yourself to 4, and my caller was 2, and so my caller say, okay, I'm pointing myself to 4, so I'm doing this, right? So that's pretty much the gist of this solution. So here I'm going to return to my caller that the position is I plus 1 still, but it's actually the next one, and otherwise I'm going to return I plus 1 normally and node. And what I want to return is call it on the head, but I don't need the index. The results just ask me for the node, and so I'll just return it. But because we are doing the recursion up, when we get to the end of the recursion, where everything was processed, we'll get the head, and so we just do 1 there, and that will give us the solution. And this solution also, you can see it goes, it's O of n also because it goes through the entire list at most once. So why is this? Yeah, so I should return node here actually instead of head. Okay, so that seems to be working. Cool. Yeah, so that's it for this solution. You can see we did a couple of different solutions. The easiest one was first, and it's always a good idea to for a linked list to think about the simplest solution first, and then always, if you can't think of anything, ask if there is a way to solve it using recursion, because it's in its nature it's a recursive data structure. So often there is a recursive solution to whatever problem involving linked list. Yeah, that's it for now. See you next time. Bye.